So how do we solve logarithmic equations with matching bases? If b, x, and y are positive numbers and b is not equal to 1, then the log base b of x is equal to the log base b of y if and only if x is also equal to y. This means that if we are taking a log with the same base of two different expressions, then those two different expressions also have to be equal. We can forget about the logs, set the expressions equal to each other, and solve that equation. But we always have to check for extraneous solutions. Remember, we cannot take the log of a negative number. That means that the expression in parentheses that we're taking the log of can never be negative. That doesn't necessarily mean that x cannot be negative, but it really depends on what happens in the parentheses once we plug in a number for x. Now, in this first example here, we're taking the log base 5 of an expression on both sides of the equation. So we can just set the expressions equal to each other. 4x minus 7 is equal to x plus 5. Let's subtract x from both sides. Let's add 7 to both sides. And we get 3x is equal to 12. Divide both sides by 3. And x is equal to 4. Now if we plug in 4 up here, we get 4 times 4 is 16 minus 7. That's a positive number. We get 4 plus 5 is also a positive number. So we are fine. This is a perfectly acceptable solution. On to our next example. Now we're taking the natural log. So the log base e from both sides. So let's just take the expressions in parentheses and set them equal to x plus 1 is equal to x minus 4. And again, I'm subtracting x from both sides, subtracting 1, and we get x is equal to negative 5. So what about x being equal to negative 5? Negative 5 plugged into the top left here, 2 times negative 5, negative 10 plus 1 is negative 9. And actually we get the same thing if we plug in x on the right. So we cannot take the log, any type of log, of a negative number. This is an extraneous solution. If we have equations where we're not taking the log with the same base on both sides, we have to use our properties and definitions of logarithms and try to rearrange and rewrite these equations in exponential form. So in our first example, we got the log base 4 of 5x minus 1 is equal to 3. That means that 4 to the power of 3 has to be 5x minus 1. So then rewriting the equation in exponential form, 4 to the power of 3 is equal to 5x minus 1. We know that 4 to the power of 3 is 64. Now we're adding 1 to both sides. 65 is equal to 5x, dividing by 5, and 13 is equal to x. Now, what happens if we plug in 13 back up here? 5 times 13, 65 minus 1. So that works out. Check. Of course, before we can actually rewrite our expression in exponential form, we have to make sure that the logarithmic term is isolated. So in this case, we have to divide both sides by 5, and we get the natural logarithm of x is equal to 7. And that is, as we know, the log base e of x. So e to the power of 7 is equal to x. And that is going to be our answer. Now e is a positive number. Raise that to any power. We continue having a positive number. So we're not taking the log of any negative number. We are just fine. Okay, on to the next example. Here we are adding two logs, and they're both common logs to the base of 10. So we can use our product property and condense this expression, and we will have the log of 2x times x minus 5 is equal to 2. I'm going to distribute my 2x, and I have log of 2x squared minus 10x is equal to 2. And remember, log is common log, and that is base 10. So 10 to the power of 2 is equal to our expression in parentheses. 10 squared is equal to 2x2 minus 10x. And we have a quadratic equation. So we are going to set that equal to 0 in order to be able to solve it. Move the 10 squared, which is 100, to the other side. We get 0 is equal to 2x squared minus 10x minus 100. And as always, first make sure that we are taking out a GCF if there is one, which there is indeed. So we got 2 times x squared minus 5x minus 50. And that gives us the fact that form 0 is equal to 2 times x minus 10 times x plus 5. X can either be 10 or negative 5. Now let's see what happens. Plugging in 10, up here we get the log of 20 plus the log of 10 minus 5 is 5. So 10 works well. Plugging in negative 5 though, 2 times negative 5 is negative 10, and negative 5 minus 5 is also negative 10. Negative 5 is an extraneous solution, does not work. Let's look at some word problems and apply our strategies of solving logarithmic and exponential equations to solve them. You have an account that pays 4.5% annually, and it's compounded semi-annually. How long will it take for your investment to double? Now, it doesn't say anything about a specific amount of money that you are investing, but it does say that the investment has to double. So whatever you end up with has to be twice as much as what you started off with. First of all, the formula we're using is the formula of compound interest. So A is equal to P times 1 plus R over N to the power of N times T. We're just going to say we start off with $1 and want to end up with $2. Doesn't matter what the amount is. So 2 is equal to 1 times 1 plus. Our annual rate is 0.045, and that gets divided by 2 because semi-annually means twice, right? Twice per year. And we don't know how long that's going to take us. So to the power of 2t, essentially we are solving this equation for the exponent. To get to our exponent, which is up here in its lofty height, we have to take a logarithm of both sides of the equation and then use our power property to bring that exponent down. And remember from the first part of this tutorial, when we do these types of things, we can use any log we want, as long, of course, as we're using the same on both sides of the equation. Now, definitely use one of the ones that are on your calculator, as you will be using that calculator towards the end of the problem. The common log or the natural log, and why not start doing this with the common log. So the log of 2 is equal to the log of 1 plus 0.045 divided by 2 to the power of 2t. We didn't need that 1 times in the front anymore because timesing anything by 1 doesn't change anything, right? But now that we have this, we can use our power property and rewrite this equation as the log of 2 is equal to 2t times the log of 1 plus 0.045 divided by 2. Now we have our t where we want to have it, and this is what we're trying to solve for, so everything else needs to go, and in order to achieve that, we are going to divide both sides by everything else that we have here on the right of the equation. 2 logs of 1 plus 0.045 divided by 2. Both sides get divided by this. And on the right, that of course cancels out nicely everything other than our t. So we have the log of 2 divided by 2 logs of 1 plus 0.045 divided by 2 is equal to t. At this point, take your calculator and let it do the work for you. And you will get t is approximately 15.58 years. So it'll take you a little more than 15.5 years to double your investment at 4.5% annual interest if it gets compounded semi-annually. In our next example, how many years will it take for an initial investment of $10,000 to grow to $25,000 and assume a rate of interest of 6%, but it gets compounded continuously? Compounded continuously means we're going to use our PERT formula. A is equal to P times E to the power of RT. $25,000, that is what we want to end up with, is equal to $10,000 times E to the power of 0.06 times T. And again, we're trying to solve for the exponent, but first we have to isolate our exponential expression. So I'm going to divide both sides by 10,000, and we get 2.5 is equal to e to the power of 0.06 t. Since we're working with e, why not take the natural logarithm this time? So ln of 2.5 is equal to ln of e to the power of 0.06 t. Using our power property, we get ln of 2.5 is equal to 0.06 t times ln of e. Now, the natural logarithm of e is, of course, 1, which already helps us simplify things. ln 2.5 is equal to 0.06 t, and now all we have to do is divide both sides by 0.06. ln of 2.5 divided by 0.06 is equal to t, and that, using your calculator, you will find out is approximately 15.27 years. But it's not only problems with money that we can solve this way. In this example, we have the population of the world in 2000 was 6.1 billion, and the estimated relative growth rate was 1.4% per year. If the population continues to grow at this rate, when will it reach 20 billion people? Now, in this problem, it doesn't tell us which of the growth formulas to use, but population growth, people are having children all over the world all of the time, so we really have to assume it goes and happens continuously, and that means we're again going to use our PERT formula. A is equal to P times e to the power of RT. Our number that we reach at the end is 20 billion, and we are starting off with 6.1 billion times e to the power of 0.014 t. Now we're going to solve this problem very similarly to the way we solved the previous one. First, we need to isolate the exponential term. That means get rid of our coefficient. And then we're going to take the natural logarithm of both sides. And now we're moving our t to the front again. ln of 20 over 6.1 is equal to 0.014 t times ln of e. ln of e is 1, and we can now divide both sides by 0.014. ln of 20 over 6.1 divided by 0.014 is equal to 0.014 t divided by 0.014. That means t is equal to ln of 20 over 6.1 divided by 0.014, or approximately 84.81 years, almost 85 years. And we started off in 2000, so in 2085 we should be reaching 20 billion of people living on this planet. All right, so much for this, and I will see you in class.